In 1984, building work began on a vast scheme to radically improve the route from London through Hatfield to the north, one of Europe's busiest traffic routes. The project involved the building of a complete new road system which incorporated a vast road traffic tunnel nearly a mile in length and the longest of its type in Europe, which took 3 years to build at a cost of £75 million. Within days of being awarded the contract in April 1984, tarmac swung into action. And very soon an administrative centre was established on site, which was to be home for 3 years to 120 contractors' management staff, 60 county council engineers, and upwards of 500 construction workers. The A1 has for over 60 years been a major traffic link between London and the north. The increasing demands for new and better roads saw the construction in the 60s of new routes to the north and south of Hatfield. But major problems needed to be resolved in the last remaining section through Hatfield, and this was to prove the most difficult. One of the problems lay in the fact that over the years the area had been built up ad hoc without thought for future highways requirements and local needs. The 1930s saw the development of Hatfield right up to the eastern edge of the bypass. The lack of planning controls which marked the period led to a jumble of development, an intermix of small industrial estates, petrol stations, shops, housing estates and flats. Over the years, various schemes were put forward, none of which offered an acceptable solution. Meanwhile, traffic on the A1 was increasing at a relentless speed. The task of solving Hatfield's growing traffic problems was entrusted to Hertfordshire County Council, who were keen to solve the national highway needs whilst addressing the local planning aspirations of the Welwyn-Hatfield District Council. The Department of Transport, who are responsible for motorway and trunk roads throughout the country, were to be the promoters for the scheme and had to be convinced of the viability of tackling the problem on such a wide front. This model shows the complexity of the overall scheme, an imaginative solution to a difficult environmental problem, a plan which would go a long way in overcoming the conflicting demands of highway, environment, and local needs. The focal point of the scheme, a 1,150-metre-long tunnel, thereby creating a redevelopment area of some 25 acres of land on the western side of Hatfield, only half a mile from the town centre, a potential impossible without the new highway. Modern advances in technology meant that the environmental and control systems necessary for such a tunnel solution were now possible. The Department of Transport appointed Mott, Hay and Anderson to look after that aspect, using their special expertise gained on motorway tunnels on the M25. All in all, some 614 detailed drawings and 11 volumes of specifications and quantities were produced to fully describe the main engineering contract. In view of the sheer scale of the operation, it was crucial to the viability of the building program that the tunnel be built in 3 stages. This would allow for maximum traffic movement around the site and for the installation of the mechanical and electrical equipment as work progressed on the main structures. The close proximity of the tunnel site to existing houses, shops, factories and major and minor roads raised an enormous number of problems, all of which required special consideration. To allow working space for building operations to proceed, vast amounts of temporary support work and extensive steel piling were needed on both sides of the tunnel. Massive pile drivers were used to push the temporary steel piles into the ground, and environmental requirements necessitated the use of noise reduction casing. The length of pile, which could be effectively driven due to the presence of a hard clay layer, necessitated the use of ground anchors to prevent unacceptable deflections developing once main excavation work got underway. This support was provided by means of drilling holes inclined at 25 degrees to horizontal every 3 meters through the sheet piles. Through these holes, 4 strands of 15.4 millimeter diameter wire was passed to form a cable 17 meters long. The top 9 meters was wrapped in denso tape to enable this section to remain free, whilst the rear 8 meters of the cable was pressure grouted to form the required fixed anchor. An early problem that had to be faced was a legacy of the Ice Age. The natural rock of the area is chalk, found approximately 20 meters below ground level, covered by a thin layer of gravel overlaid with a thick layer of boulder clay. Later, glacial action deposited 5 meters of mixed gravels and sands over the clay, allowing surface water to pond above the proposed road level. It was therefore essential to have a highly effective dewatering system in continuous operation. Stage 1 would require the construction of 242 meters of the southern tunnel structure. The northernmost end of this first section needed an early completion in order to allow the lengthy operation of diverting public utilities over the tunnel lid. As each section of steel piling was completed and the earth removed to base level, work commenced on the foundations for the side walls. Each section of the tunnel was split into panels. An accuracy of 1 millimeter was used in computing the geometric alignment of each section. This ensured not only that they followed precise mathematical curves, but also joined with the remainder. Heavy, robust timber shutters enabled the contractor to achieve a high turnaround rate and rapid concrete placement. Various opening recesses and cabling trunkways were detailed to be cast into the walls, and special timber moldings were made to cater for these. Small trench sheets were used to prevent any risk of the lowered water table causing scour behind the completed foundations. Once in place, the contractor was able to use these as a permanent shutter for the base. During building, 900,000 cubic meters of soil and gravel were excavated using 360-degree hydraulic excavators and transported by up to 50 8-wheel tipper trucks. Much of the earthwork was used for leveling and building embankments elsewhere in the scheme. A feature of the project was an undertaking that traffic would not be subjected to additional delays as a result of the roadworks. With 56,000 vehicles a day forcing their way through this busy corridor, this presented a major challenge to the organization and planning of the project. During the construction, close on 60 major traffic diversions were required to keep a free-flowing and safe route for the traveling public. This was an evolving plan, constantly changing and adjusting to the demands of the developing site. But never for a moment, through this ambitious building project, did the traffic cease to flow around its extensive operations. The logistical problems faced by the contractor were enormous. 15 cranes were brought into use of up to 110-ton capacity. The volume of concrete required by the tunnel alone was 82,000 cubic meters of 30 to 20 quality, and this was placed in just 49 working weeks. Complete bays were cast as single pours, demanding outputs in the region of 120 cubic meters per hour. Concrete production on site peaked at 2,900 cubic meters in a single week. The cup-lock scaffolding system was used for the false work to support the tunnel roof span during construction. It proved quick and easy to handle, which helped meet the strict construction schedule. Primary and secondary bearers receiving the plywood deck were usually of aluminium beams. Polystyrene voids were used in the construction of the central section of each roof span. The introduction of these voids provided valuable weight and cost economics on a structure of this size. Over 10,000 tons of steel reinforcement was required to be accurately placed during the building of the tunnel. Every new concrete batch was tested to ensure it met the required specification, both at the workplace where workability tests were carried out, and back at the laboratory where specially prepared concrete test tubes were regularly crushed to ensure the correct strengths were being achieved. With concrete and earth-moving vehicles, trucks and cranes all vying for access, mobility around the site was vital. And the maintenance of adequate servicing facilities for the various trades was a delicate balance. By building the tunnel in 3 stages, work was able to proceed at a cracking pace. Here, pipes are being laid for the internal drainage system for removing surface water which finds its way into the tunnel. Completion of each drainage run was then carefully checked and the final touches made. As the main construction work on the tunnel moved ahead, existing gas, telecom, and water services not diverted earlier had to be rerouted around the tunnel. But at the same time, full services had to be maintained. Keeping the sound level down was only one aspect of an impressive public relations operation. It was realized from the start that establishing good relations with the local inhabitants was essential. A high-profile publicity exercise was maintained from the site, with regular information bulletins and public relations features. Local industry was kept informed on changing traffic patterns, and it was of major concern to keep good lines of access to their premises. The close proximity of the British aerospace factory gave rise to concern regarding the effect on their sophisticated metal milling machines of movements caused by pile driving, groundwater lowering, or even excavation. In order to monitor the effect, a program of precise leveling was devised with the building research station, who would independently assess the results and report to interested parties. Movement detected was less than 1 millimeter. Apart from the tunnel, work was moving ahead on the 12 other structures in the scheme. There are 6 subways, 2 footbridges, and 4 large road bridges over the motorway. In addition, up to 5 kilometers of new motorway and 2 kilometers of side road diversions were progressively brought into operation. All the structures are of traditional reinforced concrete, except at Oldings. This junction formed the main interchange with the A414 and required the formation of a high-level interchange through which the A1 had to be kept in operation. To overcome the problem, use was made of pre-stressed concrete U-beams to form the main span. Lane changes provided the opportunity to construct supports either side of the existing road. As work progressed, further traffic switches diverted vehicles back under a side span. The U-beams were the largest possible to be transported by road and were lifted into position in an overnight operation. The night chosen to erect the beams was one of the worst of the winter, with lashing rain and high winds. Completion of the tunnel shell in sections allowed the M&E contractor, W.H. Smith, to proceed with the installation of the lighting, ventilation, emergency and control systems before handing back to the civil contractor to complete the section in readiness for traffic. Fixing the many lighting units to the tunnel roof was a lengthy operation. Special emergency distribution cabinets were built into the tunnel walls at approximately 40-meter intervals. And it is from these that electrical distribution was taken to each individual lighting unit, together with emergency telephones and firefighting facilities. In this way, the tunnel services were split into small units, so ensuring minimum disruption to the smooth running of the tunnel should a local problem occur. Each bore of the tunnel is longitudinally ventilated by 52 jet fans. The fans are automatically controlled in each bore by 3 air monitoring systems which assess the level of carbon monoxide in the air and check visibility. Should carbon monoxide levels rise, for example as a result of slow-moving or stopped traffic within the tunnel, the monitoring system sends a command to start up the fans in a phased sequence. At other sections of the site, the tunnel roof was being completed. Freshly placed concrete was prevented from drying out by the use of a curing agent. The organization necessary to feed the construction progress and to keep the program rolling meant that designers and builders needed to work in close cooperation, establishing and maintaining good relationship throughout the 3-year period of intense activity, with countless checks for quality of materials, correct positioning of components, and the 1,001 daily problems which were bound to occur. The scale of the future redevelopment demanded special consideration to be given to the foundations. The tunnel's center wall has been modified, therefore, in 3 isolated areas, 1 in each section, where they are supported by augured piles founded in the hard chalk substrata. In June 1984, the District Council had selected the Carroll Group of companies as their partner in the scheme to develop the land above the tunnel. The Carroll Group had proposed a bold, futuristic solution which featured a comprehensive leisure and shopping development. Elsewhere, work on the major interchanges was now coming to a final stage. Completion of the Oldings Bridge now allowed the various slip roads and local road connections to be finalized. The construction of the new bridge was only part of the story. The A414 had been catered for by an existing large roundabout in the original situation. The pattern of this roundabout needed to change several times as 6 lanes of new motorway were built through its center. By now, the final shape of the tunnel was becoming apparent, with work continuing at a vigorous pace. Inside the tunnel, work continued on constructing the raised sidewalks along both sides of each carriageway necessary to accommodate cabling and service ducts. As the gap closed, bringing the 3 sections into a whole, the completed areas were backfilled. New roads were laid over the tunnel top to reconnect Hatfield with the local road network, so enabling the temporary roads to be removed. Wherever possible, materials were recycled. These still photographs taken throughout the building operations give some idea of the constantly changing patterns of traffic movements needed during the building of the tunnel. By now, the arrangements for temporary dewatering along the line of the tunnel were being superseded by the permanent system. Use of the chalk aquifer as a means of disposal was considered unreliable, and the use of nearby rivers was preferred. The tunnel dewatering system, together with surface water within the tunnel itself, would be collected via two massive sumps built behind the tunnel main walls. Construction of the 7-meter deep sumps was itself quite an undertaking, involving substantial temporary supports and excavation techniques. Within each completed sump, massive pump assemblies were needed to lift the collected water to a system of gravity carrier drains which would transport the water to its ultimate disposal point. At Rowhide, a further large receiving sump was constructed and a further set of pumps installed to again raise the water into the nearby Ellenbrook. This minor local brook needed to be realigned and its banks strengthened to reduce the risk of scour. Encamat spun plastic mat, developed in Holland, was used to provide the strengthening. This material allowed grass to grow through the mat into the bank, so providing a natural-looking environment. The size of the brook required discharge from the motorway to be limited to 75 litres per second, and this rate was to be controlled by the use of a 1,200 cubic metre balancing pond. Valves and storage chambers were provided throughout to limit the spread of pollution through accidental spillage. Flexible construction was chosen for the main carriageway running surface. The multitude of traffic management phases and the need to construct sections on and adjacent to existing trafficked areas made this choice of material the most practical form. Based on experience gained on other similarly heavy trafficked roads, the designers decided to support the 40mm asphalt wearing course on a foundation of 205mm dense bituminous upper road base, in turn supported on a 125mm asphalt lower road base over varying thicknesses of granular subbase. In this way, a composite sandwich of bituminous material would be available to withstand the pounding from the large volumes of lorries expected to use the new motorway. The demands of the program required a multitude of concurrent activities throughout the site. Building on the line of the existing route meant that at any one time, new lengths of carriageway could be seen to be surfaced, whilst elsewhere foundations of sections of road would be prepared as areas of the site became available. Associated road bridges were progressing at high speed. The relentless need for tunnel progress continued throughout this period of activity. As sections of tunnel were completed, temporary piles could be recovered, ready to use again. The final surfacing of the roadway in the vicinity of the tunnel was not laid until the bulk of the electrical installation had been carried out, so as to reduce the risk of damage to the completed motorway surface. Here, a rolling straight edge is used to ensure that the completed road surface meets the specified ride quality. By now, the final stages of exterior work had been reached. Levelling around bridges and embankments. Final communications links to motorway control points. finishing to concrete surfaces. To provide the maximum information to motorists, a system of variable message road signs has been installed. 27 of these signs are on the A1M approaching the tunnel, and 8 on approaching roads. Normal road direction signs will be altered to divert traffic away from a tunnel bore and give the police the facility to set signs to suit abnormal traffic conditions and maintenance operations. Standard motorway warning signs are also provided within the tunnel and its approaches. Before final commissioning and the formal opening of the tunnel, local interest was satisfied when an open day allowed locals to see at first hand what the years of frantic activity had created. They could hardly fail to be impressed, not only by what they saw, but the knowledge that this vast project had been completed on schedule and with the minimum disturbance to those who lived on its doorstep. The Hatfield Tunnel was no longer just a planner's dream, but fast becoming a working reality. The day was also used as the focus of a vast fundraising exercise to benefit local charities, and many sideshows added to the attractions. Once the visitors had left, and with the official opening only weeks ahead, commissioning of the complex electrical systems got underway. A wide range of sophisticated equipment is provided within the tunnel to preserve high safety standards. The task of controlling and managing all this equipment is achieved automatically via a computer-controlled complex. As part of the wider traffic control and monitoring system, the tunnel is provided with closed-circuit television cameras and traffic detection loops, together with an array of signs. Permanent light for the tunnel is arranged in 2 parts: normal lighting in the interior zone of each bore and boost lighting at the entrances and exits. Special photometers monitor light conditions at the tunnel portal and match the natural light at the approach to that within the tunnel itself. In this way, boost light is switched in 6 stages to suit ambient conditions and thereby ensure that the eyes of the motorist are not required to open and close faster than they are able to. The performance of the photometer can be checked from within the control complex. The lighting levels throughout the length of the tunnel are graded in such a manner as to ensure that the eyes of the motorist maintain normal vision whilst entering, traversing, and leaving the tunnel. On the 10th of December 1986, the Hatfield Tunnel project was completed. The formal opening was performed by His Royal Highness the Duke of Kent, and the tunnel was now ready to take the 60,000 vehicles a day that it was estimated would flow through it.
And so in congratulating them on a task most successfully and triumphantly completed, I now have great pleasure in declaring the tunnel open.
From the police headquarters at Welwyn Garden City, a 24-hour traffic control is in operation. Cameras placed not only in the tunnel, but throughout the entire scheme give a constantly changing picture of traffic conditions. On the wall, detailed road maps show the layout of the new motorways. The success of the overall scheme required the complete cooperation of a vast number of diverse organizations. The County Council, the District Council, contractors large and small, electricity, water and gas authorities, and telecommunications. The tunnel certainly solved Hatfield's traffic congestion and allowed redevelopment to breathe new life into the town on a scale otherwise impossible. The project offers a useful blueprint for the future, but it should not be seen as a plea for tunnels in every town. However, it does demonstrate dramatically what can result when a comprehensive concept is considered from the beginning, rather than leaving individual interests to pursue their own narrower goals. It shows what can be achieved by determination and foresight in providing an integrated solution to the transport, infrastructure, and environmental needs of an area.